While we spent a little bit of time talking about what forces are and how they affect objects, it's now time to really delve into the real hard details about how exactly these interactions take place. And we're going to be doing that by starting our investigation of Isaac Newton's 3 laws of motion. Now, we're only going to get to the first couple today, and we're actually going to do them a bit out of order, but you'll see why that is later on. Let's start off with a bit of a hypothetical scenario. Let's say we have two baseball teams playing, and we've got 2 pitchers throwing baseballs that are identical at 2 different batters who are ready to hit the balls. Now, a couple things we want to keep track of. First off, these baseballs already have forces acting on them. Specifically, they have the force of gravity. They might have some air resistance acting on them. But when they come to the baseball players are going to swing their bats, and they're going to provide a new force to the ball that is completely on its own. We'll call that an unbalanced force. And what we would expect is that we've got, this guy right here, and he hits the ball, and when he hits the ball with a force in this direction, it causes the ball to accelerate in the same direction. Now, let's say we've got this baseball player down here who looks like he's been taking a few too many steroids. He also hits the ball, but he's able to hit it with a lot more force. And if he hits it with much more force, it's going to accelerate much more. So there's some connection here between the force being applied and the acceleration of an object. Now we have another scenario that's very similar, and initially we've got this baseball player. This baseball is going towards him. This baseball has a relatively small mass, inertial mass mi. When he hits it, it accelerates in that direction. But this other baseball pitcher, we'll say he's cheating a little bit and probably should be recruited based on what he's able to do, but he throws a bowling ball instead of a baseball, and that bowling ball has way more inertial mass. And when he does that, this baseball player still accelerates it, but the acceleration is much less. In fact, the acceleration may be so small that the bowling ball keeps going past them. So there is an inverse relationship between the inertial mass of an object and how much it can accelerate when it experiences a force. Something that's bigger, it's a lot harder to accelerate than something that is smaller. And combining these two ideas is really the basis for Newton's second law of motion, which says if the forces on an object are unbalanced, meaning that there is something called a net force, and we'll get to that in a second. So if the forces on an object are unbalanced, the object will accelerate with an acceleration that is directly proportional to the net force acting on the object and inversely proportional to the object's inertial mass. So first off, we say, just to kind of sum this up, we've got the acceleration is directly proportional to this. We'll get to that in a second. And the acceleration is inversely proportional to the inertial mass. So this one makes a good deal of sense. If you have an object with a greater inertial mass, and inertial mass is the ability to resist acceleration, so if you have bigger inertial mass, we should expect a smaller acceleration. But let's talk about this top one for a second. What does this mean? Well, this right here is a symbol that is the Greek letter. It's a capital sigma, and some of you are probably familiar with it from your math class, and this just means sum. So like adding together. So what this whole thing is telling you, it's the sum of the forces. Now if I want to be real specific, I'm going to say it is the vector sum of the forces, but that's a pretty long phrase, so a lot of times instead we just call this the net force. What that net force is the unbalanced part. So if we have multiple forces acting on an object, if some of those forces cancel each other out, well then if you add them together, they're not going to contribute anything. But if you have a piece that is not canceled out, that would add into and be part of this value known as the net force. But while we wrote out Newton's second law in words a second ago, usually you just see it as this equation, that the acceleration of an object is equal to the net force on the object divided by the inertial mass of the object. Now, just to make sure we remember all the units, acceleration is in meters per second squared, net force, being a force, is in newtons, and inertial mass is in kilograms. Remember, net force is not a type of force, it is just whatever extra unbalanced force that we have. But a lot of times, we actually don't see it written like this. Now, this is a real useful way of looking at it because it is very easy to understand conceptually. Now, what this is telling me is if you have more net force, if you push or pull harder, the acceleration is going to go up. If you have more inertial mass, a bigger object, the acceleration is going to go down. So this is a nice intuitive way of understanding what Newton's second law is trying to tell us. But usually, you'll actually see it written like this. Now notice it's the exact same equation. We've just multiplied the inertial mass across, so we have F, or sigma F, equals ma. Force is equal to mass times acceleration. Now specifically, we're talking about inertial mass, and we're talking about the net force. Now, one little note here about units is that since this is newtons, this is kilograms, and this is meters per second squared. If we multiply kilograms by meters per second squared, you get kilogram meter per second squared. This is literally the definition of a newton. That is what this is specifically telling us. That if I have 1 newton, I can take 1 kilogram of mass and accelerate it 1 meter per second squared. If I have 2 newtons, I can take 2 kilograms and accelerate it 1 meter per second squared. Or I can take 1 kilogram and accelerate it 2 meters per second squared, whatever the combination is. A last point we really want to highlight is over here, which is that acceleration and force are both vectors, while inertial mass is not. There's no direction to mass. So that tells us that whatever the direction of the net force is also the direction of the acceleration. So whichever way the net force is pointing, that is the direction the acceleration is going to go. Or, if we know an object is accelerating in a certain direction, then we know that the net force must be in that direction. So let's just look at a really quick, easy example. We have a 60 kilogram student standing in an elevator while it's at rest. The elevator then starts to rise, it accelerates. Applying a 100 Newton force to the student was the acceleration of the student. We just plug it into Newton's second law, and we say the acceleration is equal to the net force over the inertial mass. Well, this is the only additional force we've added to the situation, so it'll be 100 newtons up over 60 kilograms. Divide that through in your calculator, 1.67 meters per second squared up, because the net force is up, the acceleration is up. Now additionally, let's say how fast is a student moving after 1.5 seconds have passed, and if this force is constant. Well, if the force is constant and the inertial mass is constant, the acceleration is constant. So that tells us that we have this acceleration here. And from this point, if I want to know how fast, that's asking for a velocity. This is just a kinematic equation problem. So we take out our list of kinematic equations. We want to still be able to use those. Specifically, I see V0 plus AT. We plug everything in, and we get that they're moving 2.5 meters per second after 1.5 seconds. So just because we've moved on to working with forces and masses and accelerations, we still need to be able to use the kinematics we've learned in the previous 2 units. At this point, it's time to take a little bit of a detour to talk about something that's going to set us up for the next part of the lesson. So, what causes an object to keep moving? Okay, so if it's at rest and it starts to move, we know it must accelerate, it must be a force. But what causes it to keep moving once it's been accelerated? So there's been many different ways, but particularly 2 that we've historically thought through this situation. And once again, we're going to return to some old friends. The first one was back 350 years before the birth of Jesus, and it was from Aristotle, who said that objects tend to move to their natural state, which is at rest. So any object is going to tend to eventually slow down and stop. And to keep an object moving, we must continually provide what he called an unnatural force. Now, unnatural just because it was against the natural state of rest. So if you provide an unnatural force, that's something additional. And if you don't do that, eventually, like if I stop pushing on this, eventually what's going to happen is this going to move and it's just going to stop. And it's going to stop because that is the natural state. So to keep an object moving, Aristotle would say you must continually push it. You have to always provide a force to keep it moving. Period. End of story, no matter the circumstances. And this was the prevailing, thought for about 2,000 years, until the early 1600s, and about 1630, when Galileo came on the scene and changed things up a little bit. And Galileo did it in a slightly different way. He said an object's natural state, quote unquote, is not at rest, because there is no natural state. And said objects tend to maintain whatever their current state of motion is. If an object is at rest, well then it's going to maintain its current state of rest. If it is moving at some velocity, then it's going to maintain that current velocity. And so to keep an object moving, we don't need to have an unnatural force. Instead, we need to remove everything from the system, applying a force to it. We need to either remove or we need to balance everything applying a force to it so that all the external forces are knocked out and then the object will keep moving. So in this current situation down here, I've got a ball, we push with a force, it moves, and eventually it slows down. And you might be thinking, okay, obviously Aristotle is right because it slowed down and it stopped. But Galileo would say that's not enough. What we really should be thinking about is let's remove everything on the ground that causes friction, causes it to slow down, provides an external net force. And if we do that, if we push this, and then if we stop pushing it at this point when it's nice and clean and smooth, this ball would just keep maintaining its current velocity. Now, this doesn't mean there's no force on it. For instance, we know that this object probably has a force of gravity going down, at least it should if it's on Earth, and there's going to be a normal force going up from the ground, but that these are balanced and therefore do not affect the motion of the object. So an object will just keep moving if we can remove all those external net forces, or at least balance them. Well, it turns out that Galileo was in fact correct. You don't need a force to keep an object moving. Instead, we have what is known as Newton's first law of motion, which is that if the forces on an object are balanced, the motion of the object remains constant. Now let's talk about a couple things here. For first off, we say balance. So what does balanced mean? It means not unbalanced. So this means there is no net force. All of the forces must sum up to zero. There can't be any additional piece. And we say the motion of the object remains constant. What we mean by that is no acceleration. No speeding up, no slowing down, no changing direction. As long as the forces are balanced, this object's motion should, whatever its current state is, it's going to stay in that state. If it's at rest, it will stay at rest. If it's moving with a constant velocity, with the same speed and a straight line, it will keep moving in a straight line with that same speed. Now, a lot of times we'll formulate this and just write it this way. That this is basically Newton's first law stated in a mathematical form, that there is no net force. The net force of this object will be equal to zero. And that automatically implies that there is no acceleration. And now how do we know that? Because Newton's second law told us. If I've got this equation here, acceleration is the net force over inertial mass. If this first part goes to zero, well, this second part, acceleration, must be zero. Okay, now what that tells us is that although it was actually Galileo who formulated this thought and brought it all together, well, it's actually just a special case of Newton's second law. Now, to Newton's credit and to Galileo's credit, Newton recognized this. Newton compiled his laws of motions in the late 1600s, about 1687, about 50 years after Galileo brought this idea into the fore, and after Galileo's death. But when Newton compiled them, the first law, he gave credit to Galileo and basically said it was he who came up with that thought process. Newton simply built off of it and created the second law of motion, which in a lot of ways contains the first law inside of it. Now this statement, sigma F equals a zero, goes by a bunch of different names, and we can say it in many different ways. So we can say, one, there's no net force, because if there was a net force, when you add all those forces together, there should be some extra bit. That doesn't exist. We could say, two, the forces are balanced. There is no unbalanced force. We could say that the vector sum of the forces is equal to zero. That's a nice, real complicated way of saying it. And if you're not quite sure what that means, don't worry. We're going to add forces together real soon to see how we do that. But additionally, just know that remember this is sum of the forces is equal to zero. But we also have another phrase we use, which we say that the object is in equilibrium. Now, you're probably used to equilibrium from chemistry, and that was when, like, a chemical reaction is balanced. You know, you have as much going forward as you do backwards. Same sort of thing here. It implies balance. When we say an object is in equilibrium, we say the forces on it are balanced. So it's a state in which the net force is equal to zero. Now, there are two types of equilibrium. There is what is known as static equilibrium, which is just implying that the object is at rest and will continue to stay at rest. And then you have dynamic equilibrium, dynamic implying motion, which is saying that the object is moving with some constant velocity, straight line, constant speed, and will continue to move with a straight line and a constant speed. So to quickly sum up what we just kind of put together about forces, a force is necessary for acceleration, and specifically, I really should say, a net force is necessary for acceleration. If I want an object to speed up, if I want an object to slow down, if I want an object to turn, there must be a net force. But no net force, or no additional force, is necessary for motion. An object can move at a constant speed in a straight line without any net force. Or it can stay at rest, which is in motion, but you don't need a force for that either. Now, previously we discussed this claim. What causes objects to keep moving? Aristotle said an unnatural force. Galileo said, nope, don't need that. You don't need a net force. As long as there is no net force, an object will just keep moving. It will just keep doing that. But that really didn't answer the question. It just said it's not that. So what actually causes objects to keep moving, to maintain their current state of motion? And this is something known as their inertia. Inertia, which we've already talked about a bit with inertial mass because it is measured by the inertial mass in kilograms, is a property of every object, any object that has inertial mass, that causes them to resist changes in motion and thus causes them to tend to maintain their current velocity, whether that is at rest or it's moving at a constant speed in a straight line. That is what causes them to keep moving, is their inertia. The fact that they have inertial mass. And that is something we really need to get in our heads. When we hear the concept of inertia, I want you to immediately think mass. What causes an object to keep moving? It's mass. It's an inertial mass. So going back to Newton's first law of motion, this law often goes by a different name. That is often just called the law of inertia, which says that if the forces on an object are balanced, there's no net force, the motion of an object remains constant due to the object's inertia. That is why it keeps on with its current state of motion, is because the inertia resists any change. It resists that acceleration. This is a concept that you're way more familiar with than you may actually realize. Let's consider a little scenario. Let's say you are in your friend's car and you're stopped at a red light and the light turns green. So initially, you are just at rest in the car, you're getting ready to get going, and your friend, who we'll say is a bit of a risky driver, slams on the gas as soon as the light turns green. Now when they slam on the gas, the car quickly accelerates, and I should say quickly accelerates forward as the engine provides a net force moving forward. Now when they do that, what do you feel? You feel like something has pushed on your chest and pushed you back into the seat. Well, why is that? What is the source of that force pushing you backward? Well, there can't be a force. There's nothing physically there pushing you. So what are we feeling if we're not feeling a force pushing us back into the seat? What we're really feeling is we are feeling our inertia wanting or tending to stay at rest. Our body was at rest. It tends to maintain that current state. So when they hit the gas, your body wants to maintain a state of rest. The seat pushes you forward from behind due to its acceleration. And despite the fact that you're feeling that push backward into the seat, your body just wants to stay still. The reverse happens when they come to the next red light. And when that happens, let's say once again they're a risky driver and they are coming along, and now when you're moving at a constant velocity, everything seems pretty chill. There is no net force, there is no acceleration, you're just moving at a constant velocity, so your body is able to move around as if there's nothing strange happening. But when they hit the brakes and you quickly slow down, the acceleration is backward, the net force is backward from the brakes, causing the car to slow down, and you feel jerked forward. You feel jerked forward because your inertia tend to that state of movement. It was already moving, it's going to keep moving, and what stops it? Well, the seatbelt holding you back in place. If that seatbelt wasn't there, you could fly through the windshield because your inertia is resisting that change, resisting that acceleration. What you are feeling is not the acceleration. What you are feeling is really your body's resistance to that acceleration, or its inertia in action. So what are the main takeaways on this lesson about Newton's second and first laws of motion? Well, can I use Newton's second law of motion to conceptually reason and calculate how an object accelerates due to a net force? Now remember, that second law is just A, the acceleration is equal to the net force divided by the inertial mass. Now, a lot of times we see that a different way, where the net force is equal to mass times acceleration, but I want you to be careful that that's a totally fine calculation, but that is not the way to conceptually think about it. The acceleration does not cause the force causes the acceleration. Now, can we compare how an object's motion will or will not change with response to balanced and unbalanced forces? If there is an unbalanced or net force, the object will accelerate in that direction. If the forces are balanced, if they all cancel out, then the object will maintain its current state of motion, whether that's at rest or moving at constant velocity. And can we explain what causes an object to keep moving? Your inertia, your inertial mass. Additionally, can we explain what causes that experience when we undergo acceleration? That we're not feeling a force pushing us back, rather it's our body's inertia reacting to the acceleration. If something stops suddenly and you feel jerked forward, it's not your body responding to a force, it's your body's inertia resisting that stopping acceleration.